As Russell said, the title of my talk is The Audacity of Chapel, Scalable Parallel Programming Done Right. And for my personality, this is a very brash title. So you can decide for yourself today whether Chapel's really audacious or whether it's merely the title that's audacious. This is a standard statement from my lawyer saying you shouldn't bet on the stock market based on anything you hear today. Probably good advice, I think. And this is my own warning statement that I have a lot of slides, probably too many slides, and sadly no guitar solos. The embarrassing thing is I had actually prepared a guitar solo, but then it seemed embarrassing to have two in a row, kind of like wearing the same dress to a party, as I understand it. But my talk does have thematically relevant UK rock lyrics trivia. So start engaging the part of your brain that has cached away all of those key lyrics over the years, because you're going to need them. And we'll start out with an easy one. The first part of my talk is entitled I Am the Eggman. This song is, of course, I Am the Walrus by the Beatles. From which album? Magical Mystery Tour, thank you. I'm an album person, so that's a key piece of that. Yes, so I Am the Walrus by the Beatles, Magical Mystery Tour. And then for each one of these, just to tell you how the game will go, I'll give sort of the real title of that section. So this is sort of introductions. I am not the Eggman. I'm Brad Chamberlain. And as you heard, I worked on a language called ZPL at the University of Washington. Now I work at Cray, and I work on this language, Chapel. And you'll hear a lot about Chapel over the course of the day. One caveat I wanted to give in terms of myself is I think a lot of people assume because I've worked on languages my whole career that I'm a programming language expert. And I really am incredibly naive in a lot of ways about programming languages. Most of you probably know a lot more than I do. I think of myself much more as a practical parallel computing guy who happens to work in languages. And we're learning constantly from things done by C++ and Swift and all sorts of other languages. So the context for my work, I don't like talks that start using acronyms without defining them. So an acronym I'll use a lot is HPC. This stands for High Performance Computing. And if that doesn't mean anything to you, so think about parallel programming at very, very large scales, the kind of systems that Russell showed in his slides. Lots and lots of processors, lots of memories, and these are distributed across a network. So you tend to have to worry a lot about locality to make sure you're not going over the network all the time and incurring a lot of cost for doing so. Now, within HPC, performance rules. Like, performance is kind of the main thing and often the only thing, and often that's to the detriment of our community. So in particular, you'll see today some of the other programming models that people use in HPC to program these large systems, and your reaction will probably be much like mine that, gosh, it just seems like they're living in dark, dark ages. The models we use to program these machines tend to be reasonably low level, tend to be fairly fiddly, tend to be somewhat inconsistent between themselves, and I think this is a real shame. So Chapel is trying to fix this. And of course, the other context for my work is that I work for Cray, which has the tag, the supercomputer company. The next couple slides I grabbed from marketing. Russell showed you a few Cray systems. These are a few recent ones. People often ask, now that processors have gotten so powerful and so compact, Crays used to fill rooms. How big is a Cray now? And the answer, of course, is that they still fill rooms because you can put lots and lots of those even faster, even smaller processors together and make an even faster computer. So these are some recent systems. I've got some speeds and feeds up here. They're sort of really large numbers, big enough that they never even stick in my head. They're just hard to even comprehend. I was asked at the tutorial we gave the other day, who does Cray sell to? And so this is another slide from marketing that sort of covers some of the key segments of the market that Cray addresses. But generally, we're happy to sell to anyone who needs a very, very, very large calculator. Now, at this point, I'm glad to see there's so many of you here, because I can imagine you waking up and thinking, well, I don't really care about HPC programming. Why should I go to this talk? And so my challenge back to you is, so maybe you don't care about HPC per se, but do you care about parallelism and concurrency? And more, a lot of us do, as parallelism shows up on every single desktop. And what about performance? Because clock speeds are tapering off. And so if you want more performance, parallelism and concurrency are sort of the main tools available to you. What about scaling up your data set sizes? Big data and data analytics are big trends these days. If these things matter to you, HPC might matter to you as well. And what about targeting next generation processors, things like Intel Xeon Phi or Knight's Landing as it's codenamed, right? So the observation here is that next generation processors and computations within sort of mainstream or traditional computing are increasingly resembling what we've traditionally done in HPC. So even though HPC sort of in its historic sense may not matter to you, parallel computing and the kinds of things we worry about more and more probably will. Okay? All right, so time for our next lyric. This one came up over dinner with Russell the other day. Anyone know this one offhand? Things on the Wing, part 1 or 2? Part 1, sorry. Thank you for playing. The band? Pink Floyd, very good. The album? Animals, all right, you're still with me. So this section is motivation for Chapel. So the next slide is a slide that I saw early in my professional career. It was given by Kathy Yellick, who's a mentor of mine at UC Berkeley and Lawrence Berkeley. And she put up the slide, why consider new languages at all? So do we need a language, and do we need a compiler? And her argument was, if we need higher level syntax for productivity, then we need a language. And if we need static analysis to help with correctness, then we need a compiler, or at least the front end of a compiler. And if we need static optimizations to get performance, we need a compiler, a back-end compiler. And when I think about parallelism and large-scale computing, my answer to all these are like, yeah, we need all those things, of course. This is core stuff. Need maybe is strong. We are getting by without a lot of these things. But frankly, I think all of our lives would be much better if we had these things. Right, so this was good incentive for me early in my career. To start to tell you about Chapel, so it's a productive parallel programming language, and it's portable, and it's open source, and it's collaborative. And I'll come back to these points later on and add a little bit more flesh to them. But for now, it's sufficient to know that our goals are to support general parallel programming. And you can think of this as, if you have a parallel algorithm in your mind and some parallel hardware, Chapel ought to be able to help you express that algorithm on that hardware. And if not, maybe we need to tweak it some more for your sake. The other thing, of course, is to make parallel programming at scale far more productive than it is today. Now, this term productive or productivity is very loaded, right? If I ask 10 of you what productivity means to you, I'd probably get 10 different answers. So to give you a sense of the way I think of productivity and our team thinks of productivity, let me give you some characteristic answers we get from sort of maybe stereotypical people. If I talk to young students or graduates, often what they say is something similar to what I used in school and learned in school. And often these are things like Python or MATLAB or Java, right? Now, if you talk to a seasoned HPC programmer, someone who's spent their whole career in HPC, the answer you'll often get is, oh, that's that sugary stuff that I don't really need because I was born to suffer, right? And this is sort of tongue-in-cheek, obviously, but what they really mean is, I want full control to ensure performance, right? My goal is I've bought this huge, expensive machine. It's very fast. And if I can't make it run fast, I've wasted a lot of money. So completely reasonable concern. And the bias that shows up here is that people think that if something is productive, that it's necessarily going to be slower. And we can all probably think of cases in our technical lives where that's been the case. But I also believe that well-designed language concepts don't necessarily have to be at odds with performance. And I believe that's true of many of the features in Chapel. Then if you talk to computational scientists, the astronomers, the physicists, the chemists who use HPC machines, their response is typically something like, I'd like something that lets me express my parallel computations without having to wrestle with architecture-specific details, right? So they want to focus on the science and the ideas that they have, and not so much on passing messages between processors or figuring out how to wedge things into a CUDA kernel or things like that, right? So again, I think all of these are very reasonable perspectives, and on the Chapel team, we're sort of a have your cake and eat it too kind of place. So we are trying to define something that's productive in all three of these senses. Something that lets computational scientists express what they want in terms of their computations without taking away that lower level control that HPC programmers want and feel comforted by, all implemented in a language that's as attractive as recent graduates would want to program in. So over the course of the day, you can tell me whether we're succeeding at this or not. Now coming back to my title, The Audacity of Chapel, I just wanted to make sure I was using the term audacity correctly. I sometimes, just like many of us, use words incorrectly. So I looked it up according to Google. Interestingly, we define words with Google now rather than Webster's or somebody else. And the first definition was a willingness to take bold risks. And the example that was given was, I applaud the audacity of the Chapel team in attempting to create a new language, given how hard it is for new languages to succeed. Right? So this is one definition of audacity. And the second one was rude or disrespectful behavior or impudence. I can't believe the Chapel team has the audacity to create a new language when we already have C++ or Python or, pick your favorite language. And the second attitude is one that we get a lot. Like, why are you guys bothering? Like, we've got great languages. You don't need to make a new one. And in fact, one of the first papers that we submitted when I was a graduate student, one of the reviews came back and said, programming language design is dead. Like, why are you even bothering? And it was the most disheartening thing to get in one of your first papers as a student. And then shortly after that, Java hit, right? And then shortly after that, Python took over the world. And then now you see things like Swift coming out, right? So I think it's very natural for us to think like, we don't really need new languages. But I think that's showing our age and our naivete. So yeah. So this talk's thesis is that I think programming language designers, and this isn't an accusation against you or me or anything, but I think the fact of the matter is, to date, we've largely failed the large-scale parallel computing community. And I'll show you some examples in the next section. All right, so here's our next quote. Come on, you guys are from the UK. Not anybody? Radiohead, there we go. Who said it? Yeah, song? Album? Yeah, I have trouble remembering too. Very good. Radiohead, Like Spinning Plates, Amnesiac. Great song, great band, great album. So this section is entitled, For Real, the Status Quo in HPC Programming. Okay? And I'm going to start with the simplest parallel computation I can think of. This is the stream Triad benchmark. If you're not familiar with it, you take 3 very, very, very large vectors that fill a significant fraction of your memory. You take one of them, scale it by a scalar, add it to the second, assign it to the third. And if you've done any parallel programming at all, or even have a faintest idea of what it is, you probably see very quickly that this is a trivially parallelizable computation, one that we often call embarrassingly parallel, or if we're not as embarrassed, pleasingly parallel. And the idea is that you can just chunk up the vectors into approximately equal-sized chunks, have each one of your processes or tasks or whatever operate on its section of the chunk, and voila, parallel computing. Now, the way I've drawn it here is sort of my shared memory or multi-core implementation, because I just have one copy of alpha that they're all sharing. If I were running on a larger scale distributed memory machine, I'd probably replicate that scalar alpha so that everyone could just refer to it locally and not go across the network to refer to it. And then, of course, the world we're living in nowadays is we have distributed memory where then each node is a multi-core or several processor node. So we end up with these hybrids between distributed and shared memory. And so these are going to be kind of my icons for the next little while in terms of different ways of expressing this. And I want to kind of emphasize that whenever you're doing a parallel computation, I think there are sort of 2 primary things that programmers should be thinking about. And the first one is parallelism, or what in my computation can and should execute simultaneously. And the second one is locality, which is where should those tasks execute, and where should the data that they're accessing be placed. Okay? So let's look at how we write the stream Triad benchmark in HPC today. I'm going to start with MPI, which stands for the message passing interface. This is sort of the de facto standard for HPC programming today. Almost all HPC programs are written using MPI. And the font's a little bit small, so you're not going to be able to make out the details. The code in black is basically C boilerplate code. The code in red is the MPI calls. There's not very much of it here because this is such a pleasingly parallel computation. And the code in the green down at the bottom right there is the actual computation itself. Okay? So this gives me distributed memory execution. I now have stream Triad running across all of my compute nodes. And then again, if I want to make use of the hierarchy that's available in most systems today, I might throw in some OpenMP. And OpenMP, probably many of you are familiar with. It's a pragma-based markup. You can decorate loops and say these loops are parallel, and then the compiler and runtime will parallelize those loops for you across the cores. And you can see that it's just a few more lines of code. I've tagged my loops saying these are parallel loops. Go ahead and parallelize them for me. And now I have a large-scale multi-node and multi-core code that'll run across my supercomputer, which is great. Except for one thing, which is, again, this is the simplest parallel computation I can think of. And again, I want you to be thinking about parallelism and locality. And the thing to note, although you can probably barely see it, is that the concepts, the syntax, the features, the way that we describe these 2 key concerns is absolutely different in MPI than in OpenMP. And so what we end up doing is we live in this world where our brains are constantly switching between C or C++ or Fortran and MPI and OpenMP and sort of trying to make all of those fit together. And I think that's unfortunate. And then things get worse because then things like accelerators come along. And so we buy some GPUs and we do some CUDA programming. And the CUDA over here is in purple And again, it's kind of a completely new set of abstractions of syntax. It's a language extension. So we just kind of keep tacking on more and more of these things. We end up with this sort of alphabet soup of mixed programming models. So one of my theses today and of our project in general is that we think that HPC suffers from having too many distinct ways for talking about the two things that programmers should care about, parallelism and locality. And I think that this is a result of the bottom-up style of language design, right? Where we design these really big, fast systems, we design some cool hardware, and then we say, well, gosh, now we have to program it. What kinds of abstractions could we put on here to sort of get at these features that we've added? And so we come up with things. And then being HPC and being very concerned about speed and maybe not so much about productivity, we just sort of stop there. And we end up with this mishmash of programming models, and we just expect the programmers to suffer through it. And they do. Okay? So if I'm really honest, I would say, so let's roll back. Let's go from 3 or 4 or 5 or whatever down to 1. Except, of course, I'm a language guy, so rather than going back to one of these, I'm going to say, so let's add a new language. But one that'll supplant all these other ones, ideally. So this is the stream triad computation in Chapel. And it looks suspiciously probably like I've just pulled out the kernel, but this is the entire program, with the exception of 2 small expressions I've dropped, more to keep it generic than because I'm trying to hide a bunch of stuff under the covers. Right? So you can see it's much shorter and simpler. I'm not going to teach you how this works right now, although by the end of the talk you'll understand it. And the key here is we've leveraged a lot of ideas from modern language design that haven't necessarily been made use of in HPC. Okay? And the other cool thing about this computation is that this single program can be run serially, can be run as a multi-core program, distributed memory program, the hybrid distributed memory multi-core program, or really any one of a number of other ways. And this is all done through one of the expressions that I highlighted, which says, how should I map this index set and the arrays declared over it and the computations over that index set down to the system? And by plugging in different recipes there, I can end up with completely different implementations of this program. And this effectively separates the science of computing stream triad from the implementation details of mapping it down the system. And this gets back to our theme of productivity. We think that good top-down language design, where you focus on parallelism and locality first, and then think about how do I map those things down to the system and abstract those away, can set you up in a world where the compiler, the runtime, the application scientist, and the HPC expert can all focus on the things that they do best and work well together. Okay? So throughout this talk, I'm going to pepper it with little takeaways. So if you design parallel programming languages or you're extending an existing language to support parallel programming, what are some of my thoughts or experiences that I hope you'll take from this talk? And the first one is not to tie yourself into low-level architecture-specific mechanisms, because architectures change, and the more you do that, the more you make your code and your programming model brittle to those changes, as I've hopefully shown you. At the same time, it's key not to make those features inaccessible, because again, the performance-minded programmer is going to want to get down to the metal as much as possible. So you should support a way to interoperate with those models, or you should support them in sort of an inline assembly form or something like that. Don't completely do away with them, just provide a nicer alternative. All right, next lyrical quiz. The Smiths, very good. Song? I didn't see who said that. Okay, the song is I Know It's Over. Album? Queen is Dead, thank you, very good. It is easy to laugh, it's easy to hate, it takes guts to be gentle and kind. I will laugh and hate a little bit more, but then I'll try to be gentle and kind. So next we're going to look at SPMD programming models like MPI, again, the de facto standard in HPC. So most of the programming models we use in HPC at large scale are what we call SPMD. And if you're not familiar with this acronym, it stands for Single Program Multiple Data. And it's a very simple concept. You write a program, and then you run multiple copies of it. And because you're running multiple copies of it, you've got parallelism, okay? And this is what I'd call a bottom-up programming model design. You know, I design a big system, and I say, well, I've got a bunch of processors. What can processors do? They can run programs. So I'll just run a bunch of programs, and that'll be parallelism. And that's sufficient, but again, it's often clumsy in practice. And I'll show you an example here. So second simplest parallel computation I can think of, apply a 3-point stencil to a vector, which if you're not familiar with that phrase, essentially, in this case, what I'm going to ask you to do is average your 2 nearest neighbors and replace yourself with those averages. So when I say that, the picture you might have in your mind is this one on the left, where I'll take the left-shifted red elements and the right-shifted red elements and add those together element-wise and assign them to the dark orange elements in my result vector. Okay? And that's a reasonable way to think about it. That's what we're trying to do. Now, if I'm in the SPMD programming model, what I have to do is to think not in terms of the problem as a whole, but think in terms of one of those tasks or processes, right? So I am one program running on one node. I just have a fraction of the entire program. So I need to allocate a fraction of the entire data set. So rather than allocating 6 elements, as I've shown here, if I'm running on 3 processors, each one will have to think about allocating 2. And then for computations like this stencil, often what we do is we allocate a little bit of extra data so that we can cache values from our nearest neighbors and avoid sort of re-fetching them all the time. And then we have to put in some communication, of course, to update those caches and make sure we've got our neighbors' values. And only at that point can we actually do the computation itself. But again, we're not going to be writing the computation as a whole. We're going to be focusing on the little bit that we own, right? So if we look at this in terms of code, and hopefully that's almost readable, the black code here is sort of the guts of the computation that you'd have to write in any programming model. And the blue is sort of changes that had to be introduced to make this SPMD. So we start out by saying things like, how many copies of the program are running? And what is my unique ID out of those copies? And then we figure out what fraction of the problem size do we own. So take the problem size n and divide it by p. We allocate our arrays over that problem size, again, extending it a little bit to support neighboring values. And then we do some communication. If I'm not the leftmost guy, exchange value with the guy to my right. And if I'm not the rightmost guy, exchange one with the guy to my left. Okay? And then we can do the computation, again, on the local piece that we own. All right? Now, because this is SPMD, when you're writing this code, the model you have in your mind is a bunch of things are running main simultaneously. And each one of them might take different control flow through the program, but more or less, we're sort of all doing the same thing, right? So that's the way you think about this. Now, this is what we tend to call local view programming, because the programmer is focused on what does each processor do? What does each node do? In contrast to that, what Chapel espouses is global view programming. So we want you to express the computation the way you would think about it. Talk about the problem size as a whole. Talk about the computation as a whole. Leave the details to dividing it all up to lower levels of software or the runtime or the compiler. All right? And when you run a Chapel program, your mental model of the execution is a single task starts running main, as in most programming models, and then various constructs in the language create and destroy parallelism, like this for all loop that I've shown up here. Okay? So when you look at this, again, sort of second easiest parallel programming model, either one of these are things that most of us could write, right? Except for me. So I gave this talk for several months before a colleague said, you've got a bug in your SPMD program here, and this is typical. It's some sort of boundary condition thing on the extreme processors. And so with a little bit more work, we could fix that and take care of that. And so again, any one of us now could write these, even I could. But there's still some issues. One is that I've written this code just assuming sort of that n divides evenly by p, and that was kind of a nice short thing to do for this slide, but in reality, we'd have to figure out, who owns the floor number of elements, who owns the ceiling number of elements, divide it all up properly. And the other one is that, again, this is the second easiest problem I could think of. And as we start doing more complex things on higher dimensional arrays, this little bit of communication I had to do starts to explode. And to show you that, this is a 27-point stencil, so the same thing we've been doing in 3D. We're going to do a weighted average of our nearest neighbors based on how far away they are from us. And this comes from a multi-grid benchmark. And here's the code in Fortran plus MPI. If you see the colors down here, you can see that's where my 4 weights are where I'm doing the multiplication. And again, you think, well, this doesn't look too bad until you notice this call here which says com3, and you say, well, I wonder what that call does. And then you go look at it. And it's a lot of code. And it's a lot of very nitty-gritty, detail-oriented code, the kind of thing that I'm likely to get wrong. Now, to be fair, good software engineers will do a good job of tucking this away into library routines and data structures. It's not like every single program you write is going to have, hundreds of copies of this or anything like that. But still, it seems unfortunate that this is the world we're living in today. OK, so I said that I was going to be gutsy and gentle and kind to MPI. So let me give it some credit. If you think about sort of the last 20 years or so of big HPC computations and simulations we've done, MPI gets the lion's share of the credit for enabling those, right? Without MPI, we would not have been able to get those scientific results. And there's an analogy to be made here with assembly programming. So in assembly, you're explicitly moving data from memory to registers. And in MPI, you're essentially explicitly moving data, but from your compute nodes of memory to my compute nodes of memory, right? And this is a reasonable thing to do. Just like assembly, it's a very important technology. It's great for programming at lower levels, and it's great for enabling higher level technologies. I wouldn't have been able to finish my graduate work if it hadn't been for MPI, because I rode on its shoulders, basically. But I think our problem in HPC is we're sort of content to stay here. And I think that, like with assembly, we should be developing higher level alternatives to MPI, better ways of programming these systems. So the second takeaway from my talk is, if you design a parallel programming language, please don't base your model for parallelism and locality in SPMD. Again, it's sufficient, but it's a very, very blunt instrument. And when you think about sort of the richness of parallel algorithms that you could think of in design, SPMD is just a very, very constrained way of dealing with it. So instead, we propose supporting a global view of parallelism, as you've seen in Chapel, and locality as well, which we haven't seen so much of quite yet. All right. Oh, and now for something completely different. Sorry? Flight of the Bumblebee, no, wrong. Anyone else? What's that? Sousa, very good. Remember the name? Liberty Bell March. I was hoping somebody would fall into the trap of, oh, it's Monty Python, which it is, of course, but Liberty Bell March by John Philip Sousa. So this section is going to be on characterizing Chapel. I'm going to come back around to some of those one-liners I gave you earlier. So Chapel's goal overall is to create a language that's as productive as Python, as fast as Fortran, as portable as C, as scalable as MPI, and frankly, as fun to program in as whatever language you use when you're just doing programming for fun. So the challenge here, people say, oh, this sounds great. What a no-brainer. Of course we'd want that. Why don't we have such languages already? And if you ask most people, they would say, well, it's really, really hard. Like, there's some major technical challenges here. And to be fair, there are technical challenges for sure, but I don't think that's really the main problem. Instead, I think the main reason that we don't have languages like this today in HPC, or more broadly, is that there's just been a lack of long-term efforts in the community and resources to support those long-term efforts. And frankly, in the HPC community, willpower. Again, we sort of think that low-level things are sufficient and programmers are kind of meant to suffer. In addition, there's sort of a lack of co-design between developers and users. Many times we computer scientists will invent something we think is great, give it to the user, and they'll say, I'm not really interested, thanks. And the last one is patience. HPC is an impatient community. We're all about running fast. And so when you tell people like, yeah, it's going to take us a little while to build this language, people get impatient so quickly. So Chapel is my team's attempt to reverse this trend. So I mentioned earlier that Chapel is portable. A lot of people, when they hear about Chapel and hear it's being developed by Cray, they think, oh, well, it runs on Crays. And of course it does. But we realize that if Chapel only ran on Crays, that would be the death of the language, right? So the design and the implementation have both been made to be very hardware independent. The current release requires you to have a C and C++ compiler, a Unix-style environment, POSIX threads, and then if you want to run on distributed memory, some way of communicating between those processors where UDP, MPI, or RDMA are obvious choices. Now, this describes hopefully just about every computer you've programmed on, at least of a significant size and weight. So basically, Chapel runs pretty much anywhere, on laptops and workstations, on commodity clusters, on the cloud, of course, systems from Cray, as well as our competitors. And more what we've been looking at is modern processors like Intel Xeon Phi or GPUs or things like that. Okay? So Chapel is also open source. We're developing it at GitHub. It's licensed as Apache 2.0 software, so it's very permissively licensed. And I hope some of you will download it and give it a try after the talk today. Wait till the talk's over. And if you do, this is the URL to get you started with that installation. Now, this is the team that I work with at Cray that works on Chapel. There are 14 of us working on it full time. We also tend to have 2 summer interns and occasionally a visiting academic. So I wanted to take a question. How many of you think, wow, what a large team? A few of you. And how many of you think, wow, what a small team? Yeah, so this is the difference between our worlds. In HPC, this is a huge team. Wow, you have 14 people working on a language? The chief MPI implementation, as I understand it, has only ever had kind of 4 to 5 people working on it at any given time. And again, it supports all of the HPC software virtually. But if you think about what we're trying to do here, we're trying to make a language that's as feature-rich as C#, C++, Swift, Java. Name your language. We don't want to leave anything behind because we want it to be an end-all, be-all solution. And I don't know the numbers for all of those languages, but I've got to think they had more than 14 full-time people working on it. So when I think of the Audacity of Chapel, this is the main thing that comes to mind for me is like, how the heck will we pull this off with 14 people? But if you download it and take a look, I hope you'll see like we've come quite a long way already. Now, obviously it's not just the 14 of us, it's an open source effort. So there are members of the community who are contributing as well, some from the user perspective, some from the developer's perspective, and that's been great as well. But to be really healthy, to be really successful, we need to grow this community further, okay? So time for another quote. This one's an easy one again. Beatles, thank you. Revolution album. Don't fall into that trap. No, it's not Revolution number 9. Well, no, so the White Album is, as I understand it, the nickname. The real album is the Beatles, and we must be precise here. I could, but that's my understanding. So this section is Chapel in a nutshell, right? I've talked a lot about Chapel. Let me show you a little bit. There's nothing worse than going to a language talk and leaving with no idea what the language looks like. So this is a little bit of a cartoon that we use to talk about the 5 main feature areas of the language, and I'll use it kind of as a roadmap. Some of the features in Chapel we consider lower level and closer to the hardware, and I'm going to start there. And I'll start specifically with the base language, which is like if you took Chapel and you ripped out every feature related to parallelism and scalability, it's what you'd be left with. So you can think of it as the C or Fortran of Chapel, except that rather than extending an existing language, we started from scratch, although certainly picking and choosing features we thought were great from other languages. And so what I'm going to show you, just to introduce the base languages, this is a Fibonacci sequence generator or iterator. You probably have seen these in some of the more modern languages that you use. These are not iterators in the standard kind of start iterating, get next, am I done style, but more of a procedure that you say, this is an iterator. And this one takes an argument n, which says, how many Fibonacci numbers should I generate? And as it's computing them, it hits this yield statement, which basically kicks the value back to the call site and then continues executing. So we use these to drive loops. You can see I'm invoking the Fibonacci iterator over on the right there, and I'm going to print out the numbers as they come out. So each value that's yielded gets bound to f, printed out, and then I continue executing the iterator. Okay? We have these things called configuration declarations. So I've declared here a constant n, which is my problem size, and I've initialized it to 10. But I put that keyword config on it, and what that means is give me some automatic execution time command line parsing to override this value. And so by just putting that one keyword in, when I run my program, I could say, well, I don't want to generate 10 Fibonacci numbers. I want to generate 10 million Fibonacci numbers. And I can just specify that with --n, and the compiler sort of provided that for me. So the hope here is you don't have to do too much more argument parsing in your life, although you still can do it if you need to. Another thing you'll notice is that I haven't really declared types here. I haven't said what n is. I haven't said what fib yields. And this is all done through static type inference. It's all done at compile time because, of course, we care about performance. And so essentially what happens is the compiler follows the flow of the program and says, well, 10 is an integer, so I know n is an integer. And that means I have to create a copy of fib that's an integer. So it's essentially a templated iterator. And I can see that fib is yielding integers, so I know that f is an integer. And it just sort of flows through and figures out the types in this way. Now, types, of course, are important to document and to declare sometimes. You can do that. I just tend not to use that style in my slides because it's more short and shows things off a bit better. And here I started out just iterating over fib and printing it out. Chapel also has zippered iteration, where we can iterate over multiple iterators simultaneously. And here I'm iterating over the range 0 #n, which says start from 0, start counting to infinity, stop after you hit n things. So it's basically a cute way of writing 0 to n minus 1. And then I can print out a slightly nicer message. And the things yielded by that zippered iteration are tuples. Tuples are a pretty key feature in the language. We use them also for multidimensional array indexing, and they're part of the language as well. So that gives you kind of just a sampling of some of the features of the base language. It's a pretty nice language. Even if I weren't doing parallel computing, I like it a lot. So let's look at the low-level control for creating tasks and for saying where they should run. I'm going to start with a multi-core, multi-node hello world program. So when I run this program, it's going to print hello world from every compute core on my entire system that I'm running on. And I should say that each one of these codes is an entire Chapel program. You could type this in and run it. So the first thing we have here is a locales array. This is a built-in variable that its elements represent the locales or the compute nodes on which we're running. So if I launch my program onto 16 nodes, this array would have 16 elements, one for each one of those compute nodes. And I've changed from a for loop here to a co-for-all, which you can think of as a concurrent parallel loop. And what this says is, for each iteration of this loop, create a separate task to execute the loop. So if I have 16 nodes that I'm running on, I'll have 16 tasks at this point. And then what I use is this on clause, which is how we control locality in the program. And each task will evaluate the on clause and go run wherever that on clause tells it to. In this case, I'm saying, go run on your locale. And so I've created the 16 tasks and then had them go off each to their own compute node. Okay? Then there's a built-in keyword here, which allows us to refer to the locale on which we're running. And we use this to reason about the machine on which we're running. So I can say things like, how many tasks can I run here in parallel? Or what's the name of this compute node? And I'm doing that in this code, at which point I then create another co-for-all to create the number of tasks equal to the number of tasks that I can run in parallel. typically the number of cores on the node. And at this point, I now have a task running for every single compute core on my machine in just a few lines of code. Okay? Now, another key feature of the task parallel section, which is not seen in this example, is we also have data-centric ways for tasks to coordinate through atomic variables and through full empty variables. So unlike some languages where tasks just can't interact with each other, in Chapel they very much can and do. All right, and that's your very quick introduction to task parallelism and locality in Chapel. So key distinction I want to make between Chapel and the SPMD models we saw before is that parallelism and locality are distinct things in Chapel, as they should be. And probably for most of you, be like, of course they are. I mean, they're two completely separate concerns. But again, in the SPMD model, these two things are glommed together. So you can't talk about parallelism without locality and vice versa. So this is a parallel program. It creates tasks, but they won't ever leave the current compute node on which I'm running. And this is a distributed program. I'm moving around from one locale to the next, but it's completely serial. Nothing about it is parallel. I'm just sort of migrating the computation around. And of course, as we saw in the previous slide, you can compose these two concepts and create code that is both parallel and distributed. Okay? So those are your low-level features in Chapel. Let's bump up to the high-level features. So at the top of the stack, we've got data parallelism and domain maps, which is the special sauce I referred to earlier. And I'm going to just show you a really simple data parallel program. It's going to just declare an array and do some simple computation over it in parallel. One of the key concepts we have here is something called a domain. And a domain is probably one of the more unusual features in Chapel. It's a first-class language concept that describes a set of indices. So you can think of it as describing like the size and shape of an array or an iteration space. But rather than allocating like n-squared data in this case, it's just kind of like the bounds, the size and shape in indices. And we use those domains both to declare arrays. So here I've declared array A in terms of my domain D. Now I have n-squared data. And we also use them to control computation. So here, for example, I'm using a for all loop to say for all the indices in D, calculate some value based on a function of I and j. Now the for all loop sort of falls between the for loop and the co-for all loop. The for loop was serial. The co-for all loop used a task per iteration. If I had 1 million elements in this array, I wouldn't want to create 1 million tasks. That would probably be overkill. And the for all loop basically says, use an appropriate amount of parallelism for this data structure, typically something on the order of the number of cores to which the data structure is mapped. So if I'm running this in a shared memory mode, which is the way it would happen here, I'll probably use the number of cores to execute this for all loop and have them divide up the iteration space. But I can also go in and throw in one of these domain maps we saw earlier. And this says, again, how should I implement this domain, this index set? And here I've said, let's use a cyclic implementation, which deals out the indices to all of my compute nodes in a cyclic manner. And so then my array is also distributed now. And my loop is also distributed. And I'll end up using all of the cores across all of the nodes to which the array is distributed. And this gets back to this notion that I've just changed one little bit about this domain's declaration, and I've completely changed the science of computing this array A, right, without actually going in and mucking with the loops and the computation itself. Right, so this is a key theme in Chapel. All right, so if you haven't got the picture for domain maps, we want programmers to be thinking this global view, thinking about their problem as a whole. But of course, something has to map that down to the architecture, and that's the role of the domain map. It chunks things up and figures out what should each locale allocate, what should it execute, and that's its role in the language, a recipe for implementing parallelism. Now, the cool thing about domain maps, and from an implementer's point of view, the really challenging thing is this philosophy. So of course, Chapel's going to come with a standard library of domain maps, things like block and cyclic that you're going to use regularly in computations. But if you are an expert, you may have a certain way you want to lay out your data, either distributed across nodes or within a node's memory. And a key feature of the language is that you can write your own domain maps in Chapel. And in fact, you do this in Chapel itself. So you just say things like, how do I allocate this array? How do I iterate over it? How do I iterate over in parallel? How do I random access it? And if you provide that interface, the compiler can target it, and you can plug it in as one of those domain map clauses as well. The third thing, and this is the thing that's probably slowed our progress down the most, is we held ourselves to a standard that all of our built-in arrays and domains, even the simple, just completely local one, would be implemented using the same machinery. And this is sort of an instance of wanting to eat our own dog food, right? We didn't want it to be that the first time you wrote a domain map, your performance just fell off a cliff because you fell out of the compiler's knowledge. So to hold ourselves accountable, we sort of made sure that all of our arrays were implemented with the same framework that an end user would use. Okay? And this is part of what we call Chapel's multi-resolution design. It says we've got multiple tiers of language features, higher level features for productivity, lower level features for control, and you can implement those higher level features yourself within the language in terms of lower level features, so they interoperate together, and so you can go back and forth between different feature sets as needed by your program. Now, this is a pretty complex topic, but there are two other main features in language that are also multi-resolution in this way. You can write your own parallel iterators. So those for all loops that I said, you can specify the recipe for how many tasks should that create, and where should they run, and how should we divide up the iterations between them. And the other one is if you have a new compute node architecture that we haven't anticipated, you can specify how the locales are mapped down to that. So you can say, for targeting this architecture, here's how you allocate memory, here's how you run tasks, here's how you communicate. And by specifying that, we can then run on your architecture. Right, so we've tried to make the language future-proof by allowing end users to control these very important but very fiddly policy details that are so important in parallel computing. So going back to takeaways, if you design a parallel language, create alternative ways of expressing parallelism and locality, right? Most of the time these are pragmas, function calls. I think these are core concerns and they deserve first-class language support. The second is, and this is biased a little bit, but support these first-class index sets, these domains that you saw. We haven't really gotten much into the domains today, but they're an incredibly expressive concept for users. You can succinctly say things like take a slice, a sparse slice of a dense domain, express it very naturally, and you're expressing a lot of parallelism there. And they also give a lot of important semantic information in the compiler. And the last one is to support multi-resolution features. So give the users the ability to develop their own parallel policies, because you're not going to be able to anticipate everything they might need. All right, time for a lyric. Going back to the classic days. Led Zeppelin, thank you. Song? Close. It's Your Time Is Gonna Come. I should have asked for the album off of Led Zeppelin. All right, so this is looking at some results, the computer language benchmarks game. Many of you may know about it. Some of you may groan when you think of it. If you're not familiar with it, it's a website for supporting cross-language comparisons, or really cross-benchmark comparisons, because it only claims to measure what it's measuring, and what more really could it do? So there are 13 toy benchmarks written in a bunch of languages. It's important when you look at this site, if you're not familiar with it, to take it with a grain of salt. Your mileage may vary. Your computations are going to be different. Your architecture is going to be different. Your compilers might be different. But that said, I think it's still a really nice site. I wish there were a lot more of these, frankly. It's one of the only such games in town, and it's really hard to compare languages. So I like that this site has made a great attempt at doing this. The site started taking Chapel entries, and we started submitting them, and we took an approach of striving for elegance over heroic programming. And when you look at some of the fastest entries, many of them are quite heroic. So ideally, we wanted to create copies where you would say, like, oh, you want to know how that benchmark works? Go look at the Chapel version. It's a pretty clean implementation. Now, if you look at the site, one of the things it does is it sort of ranks language in terms of how are they doing in terms of speed. So it, like HPC, is kind of very speed-oriented. And so the fastest language is over here on the left. It's C. Then you can see Rust, C++, Ada, and then Chapel. So we're in pretty good company. And then after that comes Java, Fortran, Swift, Go. Now, I don't want you to draw too many conclusions from this again. It's just a game. It's just a few benchmarks. And frankly, these rankings change fairly frequently. But I want to show you that we're sort of in the running with these other languages. I'll also point out there's obviously a big gap between these first three and the others. And that refers to the heroism I saw that I referred to earlier. If you look at some of the C and C++ codes, they're codes that most of us probably wouldn't write or even have the expertise to write. Although, some of us could, and with effort, we all could. You can look at the results in terms of execution time or code size. We care about both these things together, and the website doesn't provide a good way of doing that. So we tend to plot these scatter plots saying, how are we doing overall? Where sort of the ideal would be in the lower left, where you would be the fastest and smallest implementation. And so we go through and compare, how are we doing against these other languages? And generally, we think we're doing well. Our performance is pretty good, and generally, we're much more succinct than almost all of them other than Scala and Python, I believe. Now, more important than this, if you go look at the site, promise me that you will actually go in and look at some of the source code, because it's really revealing. The Chapel case has some nice things like you've seen today, like the co-for-all loop, right? And then you look at like the C version of this same benchmark, and there's all this like schedule, get affinity, blah, 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 blah kind of stuff. Again, it's pretty heroic code. I'm quickly running out of time, so I'm going to start accelerating. This is an easy one, I think. Still haven't found what I'm looking for. This is U2. So let's look at some scalability results here. In the interest of time, I'll say these are some important benchmarks for communication idioms. This first one does sort of a bucket exchange type of thing. MPI and SHMEM, these are sort of the reference versions, so this is kind of what you would expect today. And this is the Chapel version as of our latest release a couple weeks ago. So you can see it's doing quite competitively at this scale. This is another one, random access, random updates across an array distributed across the whole machine. Here, higher is better. And as you can see, as we add nodes, Chapel's actually outscaling MPI in this case. And arguably that's because we're more able to get at the native hardware resources of the network than MPI is able to. This is my hardest one here. I think you're going to need help, unless there are any Scottish music fans in the room. So this is the Twilight Sad. That summer at home, I had become the invisible boy. This is my summary. So this talk's thesis: programming language designers have largely failed the large-scale computing community. Parallel features have typically been an afterthought. We design languages and then we sort of glom things in using libraries, pragmas, and extensions. They're rarely first class. Even when a language is designed for parallelism, they typically don't think about large-scale distributed memory parallelism, which is, of course, what my field cares about. Or when they do think about that, they tend to be domain-specific and not really appropriate for completely general parallel programming. So I think we can do better, and by we, I mean both, by we, I mean both the HPC community and sort of all of us as you become HPC programmers as well. We think Chapel's an attractive candidate, obviously. We think it's an attractive language for end users. As you've seen, it's able to achieve competitive performance. I don't want to blur things too much. There's still more work to be done in terms of performance and scaling. These are some initial results. We're not done yet. This is the recap of this talk's takeaways, but you've seen it as we've gone, so you can look at this sort of after the fact. And I have a couple slides on challenges, but I think in the interest of time, I'll go right past those. The Smiths, thank you. Good answer. I can't actually say that. Russell and Ruffians from Mita's Murder. So some resources after today if you want to scratch our name on your arm. If you want to stalk us, we're on Facebook, we're on Twitter, we're on YouTube, and we've got mailing lists, of course. If you want to watch another Chapel talk after this and you want to hear from someone that's not on the Chapel team, this is one of our users who gave a keynote at our workshop last year. It's up on YouTube, and it's sort of, he's an astrophysicist at Yale. It's kind of his take on the Chapel language from a user perspective. If you're a reader, the best thing to read is this chapter from this book. I don't know that the book's available over there. It's also available online. And if you've got too short an attention span to read a chapter, like many of us nowadays, these are some key blog articles. So the last thing I'll say before going to questions is if you're interested in some swag, we've got some glasses or screen wipes up here and some stickers. They're up here on the bottom of the stage. Please help yourself. I'd just as soon not take them back home. And I think we've got time for a couple quick questions. And I want to see the mic balls in action because we didn't get to really see them much yesterday. So please, questions.
Whoa, yes. Hi, thanks for the talk. Have you, before designing a new language, have you looked through kind of frameworks, libraries that kind of try to achieve what you achieved with the language itself? And what would be the main differences that they failed to deliver? So thinking, for example, in C++, now we have threads, atomics, we can control that, but there is no specific way of having a thread pool which was delivered through libraries like libdispatch or thread building blocks by Intel.
Right.
So do you have any type of this comparison between Chapel and as a new language and frameworks within the HPC community?
Yeah, so I think that's a really good question, and I think it's a hard one to answer succinctly because, of course, anytime you start doing comparisons, it sort of explodes on you. But I guess I'll say, certainly we did look at existing frameworks and languages, and many of us had worked on failed languages ourselves as we were designing Chapel. And we spent a lot of time asking about the questions, why did this language not take off, and what could we do to address that? And we also looked at key features from languages that that's a key thing, and maybe it didn't have these other things, but let's bring that in. I would say that, if I were to broadly say what did previous approaches not provide that Chapel does, and that we thought was important, I think it goes back to that SPMD model aspect. So if you think about C++, at least as I understand it, and I don't keep up with the latest versions of the standard all the time, there really isn't any way to talk about sort of large-scale distributed memory and parallelism across that distributed memory and such. And so you end up being forced into the SPMD model, which again is sufficient, but really not a productive way to program. And that's not true just of MPI, but really of the vast majority of parallel program models that have been developed, both as languages and as libraries or frameworks. So maybe I'll leave it at that for this, and we can talk about this more offline if you're interested.
Okay, thank you.
Austin, you have to come closer.
I was wondering yesterday whether the threat of being hit by a ball is why people don't ask questions.
That's part of the fun, right? What's Chapel's take on resiliency if a node fails, right? Is that something you concern yourself with, or is that a lower level detail that you don't worry about?
Yeah, so resiliency has been a really key theme in HPC recently. As these machines get bigger and are built more and more with commodity parts and just have thousands of parts, as you saw, the chances of failure are high, and so resiliency is a really important research area. We haven't done a lot with resiliency. We've had a couple of ideas about things one could do in Chapel, like the domain maps I talked about, are really saying, how do I implement an array? Yeah. Could I create a resilient domain map that sort of did some sort of replication under the covers? I think you could. We haven't pursued it much ourselves. I'll say that we tend to have a fairly full plate, as you've seen. And so our sort of secret hope is that resiliency will be taken care of by the operating system and the hardware, and not something that will ever get up to Chapel's level. That said, I think there are things that one could pursue here. We just haven't had the chance to ourselves so much. Yeah, good question, though.
Do we have any other questions?
I got one over here.
Go for it.
I should also say that I'll be around the rest of today and all of tomorrow, and I don't really know anyone here, so I spend a lot of time just kind of standing by myself. So feel free to come ask questions, talk to me anytime over the next couple of days.
What does success look like for the Chapel team? And I suppose included with that is what's uptake been like?
So the success for us ideally would be adoption, right? So that HPC programmers in 10 years thought of Chapel as a viable alternative to MPI, or mainstream programmers for that matter. Like, we'd really like to grow out of just the HPC community. So that's success for us. But as I said, language adoption it's obviously a very, very challenging problem. Even if you had the perfect language, there's so many social challenges, and that's one of the slides I skipped past, that would prevent or could prevent a language from being adopted. You really just can't guarantee anything. So the sort of runner-up prize there would be to influence other languages that go on and become successful, or extensions to existing languages, and have them say like, they've really done that right. We should bring that into C++, for example, or something like that, right? That would be a good consolation prize for us. And as far as uptake, people often ask us how many Chapel users are there, and I don't know exactly how to answer that. The number is today quite small, and that's not surprising because, frankly, if you were to ask me any time over the project, should I use it for my key computation, I would say, yeah, probably not yet. Give it a try, give us your feedback, but wait until we get a bit further. And as we're just now getting to the point where I can start to say to people, I think it's starting to be ready. If you're willing to kind of roll up your sleeves and get your hands a little dirty, I think it's starting to get to that point. I will say quantitatively, we do 2 releases per year. We get about 3,000 downloads per year. So that gives you some sense of interest. But that number really needs to be more like 10,000 or more in order to really be healthy, I think. So.
And we'll have to make this one the last one for time purposes.
This is a silly one, but a follow-up from the last one. Mm-hmm. Do you intend to grow a beard?
Oh, yeah. I actually just shaved a beard just for you guys. Every time we do a release, I stop shaving because I just can't find the time. And we just released a couple weeks ago, and so I had like a month-long beard, which is kind of probably the biggest beard I've ever had. And I was like, well, I need to look good for these ACCU guys. So, yeah, but I can bring it back if that's what it takes to get you to look at Chapel. All right, so this is my last quote of the day. Get up, eat jelly, sandwiches. So what I'm saying is have a great break and get some yummy snacks. Thanks very much.